All right. So let's continue the idea of modifying surfaces. Now we can model metal electrode surfaces, but people have not been really happy with basic metal modifications. Most people have now turned to carbon surfaces because it turns out the much richer type of processes can be done on carbon electrodes. And because carbon electrodes is a much cheaper substrate fundamentally, they thought if we're going to modify the surface, we might as well modify a cheap surface rather than an expensive metal surface. And that's not completely true. In many cases, you're still using metal electrodes, but a lot more people are using carbon electrodes, particularly for analytical purposes when they modify them. One of the reasons is that they're very rich chemistry that you can do on a carbon surfaces. Carbons can be modified to have lots of different types of oxidized surfaces. I've got something in my notes. You can think of a carbon surface as being sort of this group of phenyl rings linked together in this various ways. You can think of them having carboxylate groups on the surface, or you could think of them having carbonyl groups on the surface, or phenyl groups on the surface, or you can think of them having sort of furan type rings on the surface, or linked processes on the surface. So there's lots of different, very rich chemistry that you can employ. So a lot of these things are just basic things that you could look at in organic chemistry and say, what could I do? So what sort of transformation could I apply to get a covalent bond formed here at, say, this carboxylate group? Carboxylic acid is good because it can be used to form amide-type bonds. And one example, if we took this particular part and we added thionyl chloride, you get an acid chloride, which now is able to be modified. If you take that acid chloride and you add something like CH3COCl, you get let's see, what am I doing here? Yeah, you get this activated species here, which is now not very stable. You add an amine group here with a aromatic or some sort of R group on there, and you get this amide form. Amide bond here, and that's now that R can be something that you can further modify or maybe the final result, but it's pretty easy to add almost any amine type group there. Now that's a very stable bond, will not be easily removed. It's not susceptible to heat or acid so much, very stable. There's also a reaction that's used quite a bit. It uses a carbodiimide type attachment. The idea then is you'd form this activated species like this that's now much let's see. It's got these cyclohexyl groups on this diamide bond, and this is now is easy to remove this particular species and attach other things to it, and these are very gentle conditions. You don't have to use for example, this thionyl chloride is fairly harsh process. This is a much easier process where you use this reagent under normal aqueous conditions. People have tried this, like I said, they've tried to make monolayers. They put different R groups on there, try to promote chiral reactions. Chiral reactions don't really work that well. The basic problem with chiral reactions on a monolayer surface, there's just not enough chirality on the surface. There's not enough molecules to really affect the process. Some small, slight enantiomeric excesses have been reported with chiral reactions, but not enough to make it worthwhile. So surface modified electrodes are not used for promoting chiral reactions as monolayers, but as catalysts, they actually work pretty well if you use catalysts that are appropriate. One example is using enzymes. Enzymes, of course, are just biochemistry catalysts, and enzymes can be readily attached to surfaces using some of the chemistry we've talked about. And the reason is, for example, you could take a carbon surface, a carboxylate covered surface, expose it to this carbodiimide. That's what this part is this carbodiimide group. And expose it then to a diamine surface. And then go through another step in which there's this thing called sulfur NHS biotin. And what this does is it reacts with amine groups and adds this biochemistry reagent called biotin to it. So what you're doing there is you're going to add this, from this carboxylate group, you're going to add this amine group on there, then you're going to react that to form this biotin group. Now biotin is a biochemical molecule, and it turns out that the biotin-avidin conjugate is the strongest biochemistry conjugate they've known. It's very, very strong and stable. It's not a covalent bond, but the attraction between the avidin and biotin is very stable. Biotin and avidin can complex 4 biotin molecules too. So what you can do is you can use this vitamin, which is biotin. You can actually see it in your bottle of biotin, your vitamins. You'll see biotin as one of the things that's in there. And then you get this long chain, which is this part here from the R. Then you've got this biotin attached to it. And then you can add some avidin to the system, and we'll show avidin in this way with kind of this curved corners. And you make this, if you apply just the right amount, you'll form this surface like this, in which one avidin is now stuck to the biotin. There's 4 sites to attach a biotin to the avidin, so you could put 4 avidins on that one biotin, but usually just one is put in there because of the way you've done the experiment. Then what you can do is you can take an enzyme molecule that has attached to it a biotin, and it turns out you can buy enzymes now commercially that have biotin on it. They're called biotinylated, or you can do some biochemistry to actually attach a biotin to the surface. It's not that difficult either. And the idea is now you can have a surface like this. You have at the beginning of the molecule, you have this amide bond, and then a chain with a biotin and avidin, and then your enzyme and biotin are attached like so. So you've got this long chain, biotin, avidin, biotin sandwich, and then your enzyme. So your enzyme now is able to do some chemistry, and it does what it does naturally very well, acts as a catalyst for biochemical transformations. And for example, you could use a glutamate dehydrogenase is one example of an enzyme that is very selective for glutamate molecules and turning it into a dehydrogenase version of an alpha-ketoglutarate. And in the process, it takes an oxidized species and turns it to a reduced species as a co-substrate. So it takes glutamate and catalyzes the formation of alpha-ketoglutamate. And this oxidized molecule is often, in nature, it's an NAD, nicotine adenine dihydrogenase, or nicotine adenine dihydrogenase, and then there's the reduced form is NADH. Basically, you've added a hydride to it, and that's what's in nature. But in a lot of, actually, it turns out that you can use other things like quinones can be used to drive that reaction, and so on. So basically, the enzyme oxidizes this material, and the process uses a oxidizing agent to restore the enzyme back to its original state. And so we get a net oxidation. So the enzyme catalyzes this by using another molecule to do the reaction. The advantage of having this modified electrode is now that you can you can make a sensor for glutamate oxidation, or for glutamate. Now glutamate can be oxidized with this enzyme. In fact, it can be oxidized on an electrode, but it takes a very high positive potential. And when you apply very high positive potentials in most conditions, you're going to oxidize almost everything else that's in the solution as well. So you have a situation where it's not a good analytical process. You oxidize the material, but you also oxidize everything else. So looking at the current for the oxidation of glutamate is not a very selective way to detect glutamate. But if you couple the glutamate oxidation by using an enzyme, you can take and add to your system, in addition to your glutamate, you can add an oxidized molecule like NAD and detect reduced molecule on the surface. So the only way we're getting red out of the system is when glutamate is being oxidized. So by detecting red, you're essentially detecting glutamate. So and because of the way the enzyme works, in this case, there's a one-to-one correspondence between the amount of glutamate that's being converted to alpha-ketoglutamate and the amount of red that's being formed, in this case NAD, or it might be a hydroquinone or something like that. And so this is one way to make a sensor for a molecule like glutamate that would not be able to be detected otherwise. And that's what they're doing it with. Well, we'll stop here. We still have some more left on that, and we'll finish that on next Monday. And probably go over that fairly quickly, actually. And we'll start again then with Chapter 8, and as I said, Chapter 10.